Hi all. Today let us discuss about short circuit and open circuit tests on transformer. The main purpose of these tests are like to know the equivalent circuit of the transformer, which further tells us what are the core losses and what are the full load copper losses or I square R losses. Okay, this is one thing. Another thing is whenever any client any client orders a transformer from OEM, he gives some specifications like my no load losses should not exceed some value, should not exceed some specified value. These are one thing, and at the same time my transformer whatever I am ordering, it should not have a I square R losses beyond certain value. In India, for power transformers, CEA standardizes those losses. Those losses, as per CEA, these are the values on transformers. Let us take if it is 765 400 kV and by 333 kV 500 MV auto transformer single phase, these no load losses should not exceed 80 kilowatts. At the same transformer, I square R losses at rated current and rated frequency. Rated frequency means that is at 50 Hz in India at 74 degrees should not exceed 335 kV, 335 kilowatts. At the same time, no load loss for 400 by 220 by 33 kV, 500 MVA, three-phase auto transformer should not exceed 90 kilowatts. And I square loss should not exceed 375. These are the values for other remaining transformers. These will be useful for your interview. And we have to see one thing: once rated voltage and rated frequency fixed, these core losses are fixed. Core losses are fixed. Generally, students gets confused. Someone says, "What are the constant losses?" Constant losses are constant losses. Immediately they will tell core losses or iron losses are constant. Means, but these are constant when voltage and frequency are constant. If some transformer is designed for certain value of voltage and frequency, at that voltage and frequency, these core losses are fixed. But if we change the voltage and frequency, these core losses will vary. You can see this is a eddy current losses formula where it is dependent on frequency and Bmax indirectly dependent on voltage. Likewise, even hysteresis loss also is dependent on frequency and voltage. You can see here. That is the reason why if Indian transformer designed for certain frequency and if we use the same transformer in America, definitely the core losses will change. At the same time, one transformer is designed for some certain voltage, and if we change the operating voltage or if we connect the transformer to some other voltage, core losses will change. Those core losses are not constant. You have to remember very clearly that if voltage and frequency are constant, core losses are constant. If those vary, core losses vary. Okay, this one point you should keep it in mind. And to get uniformity across the transformer manufacturing, there is a one standard IEC 60076. IEC means International Electrotechnical Commission. As per this standard only, transformers gets manufactured all over the world, so that one transformer is designed and it is transported to another country, it will work easily. That is a one point you have to remember. Now let us come to our academic point or gate preparation point of view. You see, open circuit arrangement. Here we have connected LV side to voltage source, and HV side we kept open. Why LV? Why we have done open circuit test on LV side? Means let us take 2000 by 200 volts transformer. In this case, it is difficult to arrange 2000 volt source compared to 200 volt source. So, power supply arrangement point of view and at a lower voltage itself, we were able to get the test done. That is the reason we keep open circuit test on LV side only, and HV side we have to keep open. That is the name itself, open circuit test. Here the arrangement, you can see, to measure the input current, how much it is drawing from the source. We kept one ammeter in series. How much voltage we are applying to the transformer. We kept one voltmeter, and what is the power it is drawing from the source. To know that, we kept one wattmeter. We know that this is the equivalent circuit of the transformer. This is primary side, resistance and reactance. These are the shunt parameters, and these are the secondary side, resistance and reactance referred to primary side. Shunt parameter. First, we have to know from where these shunt parameters have come. Let us take, this is the transformer. This is the transformer. When it is connected to no load, still it draws some current. Why? Even though there is no load connected to other side. What that current is, for what purpose that current is being utilized? There are two purposes. One is it creates magnetic fields which links the secondary winding. To create magnetic field, it uses the current. That is called magnetic current. Magnetic current, nothing but Im. In some books they refer to I mu. Second one is IC or I iron. Second one is to represent these core losses. Core loss means eddy current losses, hysteresis losses. We keep one current component as IC or I iron. These two components get a vector summed, and it will be drawn from the source in the form of I naught. This Xi naught represents magnetic field current load. Magnetic means uh, the current which is drawn from source in form of I mu is utilized for creation of magnetic field. This resistance is nothing but representation of core losses, that is iron and eddy current losses. Here we have to keep one thing in our mind, that whenever transformer is connected on no load, no load, the current is always lags source voltage. Why? Why? Because this is voltage. So this is applied voltage. This is I mu or Im. The current which is used for creation of magnetic field lags voltage source by 90 degrees. And another component which is going through this resistance. Resistance means representation of iron losses. This is, it is in phase with the voltage, that is IC. So IC is in phase with voltage source. IMU is 90 degrees lagging. Okay, the summation is, it is not 90 degrees, just little bit high, like this. This is I naught. Why? I mu or magnetic current is much higher than core loss or iron loss component. That is the reason this is vector sum. This will come like this only. So whenever you have given like I naught, if they give one question like this, I naught is 100 amps. Select I mu, comma I iron from following options. How you will select? Let us take A, it is 90-10, B 50-50, C 10-90. What you will select? We have to select option A. Why? Because I mu, that is magnetizing current, is much greater than core loss component. So this is a representation, and you may observe that the secondary is open in case of open circuit test. So what happens? There is no load on this side, 0 amps. So the whatever current drawn from the source, it will go like this. As the current is very less and these parameters are, the drop across this parameter is very less, and we can neglect these series parameters for simplicity, and the result circuit you can represent like this. Means voltage is applied across these two branches. One is across R0, one is across X0. Means our voltage is used for magnetizing the core and to meet the core loss component. So from the arrangement circuit, we have three parameters in our hand. What are they? They are, first one is input power, the input power, how much watts it is drawing. Second one is voltage, voltage. Third one is how much current it is drawing. So current is nothing but directly I0, total current. Voltage is input voltage. This meter reading is nothing but power dissipated across this R0. So we can find R0 easily. How? Our R0 is equal to nothing but wattmeter reading by input current square. You will get R0. Okay. Once you get R0, and you can get Z, which is nothing but V by I0. You will get Z. You got Z and R0. You can easily find out this X0. How? X0 is nothing but Z square minus R0 square under square root. We know the current here, we know the parameter here, we know the total impedance, and from total, these are only resistance component. If you remove from total impedance, you will be left with X0. So in this method, you can find out shunt parameters, nothing but R0 and X0. Or you can find out admittance. From admittance, you can remove conductance. There you will get this susceptance value. Any method is okay, but if you use whatever the method you are regularly using, that will be comfortable to you. And now we will go to short circuit arrangements. Short circuit we always perform on HV side. HV side. Why? Let us see this example. 2000 by 200 volts transformer. Let us take, this is 2 kVA. Means this side 1 ampere it will go, this side 10 amperes. If you perform this short circuit test, means in short circuit test you have to ensure that full rated current is flown through the transformer. Here full rated current is 10 amps, here full rated current 1 amps. So to perform short circuit test on LV side, you have to get a source which can supply 10 amps. But if you perform HV test on if you perform short circuit on HV side, you need to get a source with 1 ampere. Just for example, I told in practical this is much higher. The short circuit current is much higher. It is very difficult to get a practical source which supplies that much current. But in practical, you will get a voltage source with higher rating easily than current source with higher current. That is the reason generally we prefer SC test on HV side. And one more thing here, HV side will perform, but we don't need that much voltage source. Why? Because to ensure rated current, we need very less voltage. Let us see how. Let us see how it happens. Listen carefully here. Let us take there is a one transformer like this. It is 100 volts through some impedance. It is supplying load. It is supplying load 90 volts. This Z is 1 ohm. Here rated current is 100 minus 90 by Z, nothing but 10 amps. Now let us take, we have shorted this secondary portion, means shorted this load portion. And so what happens here, the equivalent circuit is 100 volts. This is Z impedance 1 ohm. This is shorted. Here, if you keep 100 volts, it will result in drawing of 100 amps, which can damage the circuit. But our rated current is only 10 amperes. To flow the 10 amperes, we need only 10 volts instead of 100 volts. That is the reason why we need in SC test with less voltage rating source with this much current. Now let us analyze the SC circuit test arrangement. Here our HV, this is our LV side we shorted. Here to measure the input voltage we kept one voltmeter. To measure the input current, how much it is drawing from the source, we kept one ammeter, and we kept one wattmeter. Here also, like like open circuit test, we got three parameters: in voltage input, current input, and wattage. How much it is drawing from the source. Here the normal equivalent circuit input impedance. This is primary impedance. This is second side impedance, and these are the shunt parameters. Here we can see when voltage and F are at rated, our iron losses are constant and they are at specific value. But in SC test, we apply very little voltage at rated frequency, and because of the reason iron losses are very much lower than copper losses. That is the reason we don't consider this shunt branch. And also, if we apply less voltage, magnetic current also very much less, and iron losses are very much low. Because of these two reasons, IMU is very less and IW is very less. So we can ignore this branch. As a resultant, the equivalent circuit will change like this. This shunt branch has been removed. Now, whatever current is flowing, it is flowing through primary impedance plus secondary impedance. Now, what are the parameters we have in our hand? One is VSC and ISC and P copper losses. Here, from these two parameters, we can find it out VSC by ISC. We can get resultant impedance, series parameter resultant impedance. And we know copper losses and we know short circuit current rate, that is rated current, ISC, nothing but. From this we can find out R equivalent, nothing but P copper losses by I rated current square. You will get R equivalent. Once you have R equivalent and Z equivalent, you can easily find X equivalent. XL equivalent, nothing but ZSE square minus R equivalent square under root. So from this calculation, you got X equivalent, R equivalent. From open circuit test, you get R naught, X naught. From a short circuit, you get X equivalent, R equivalent. But here is the catch. Here, in open circuit test, you get these R naught and X naught on LV side. But in short circuit test, you get on HV side. If you want to represent, you have to shift all these parameters to either one of side. How you will do it? Let us take this. If you want to represent on LV side already you have R naught, X naught. HV side you got R equivalent and X equivalent. To represent those values to LV side, just you do R equivalent by voltage ratio square. At the same time, for X equivalent by ratio square. In this method, you get the entire transformer equivalent circuit. At the same fashion, you can represent entire circuit on HV side also. There just you have to multiply R naught into ratio square, X naught into ratio square, and R equivalent, X equivalent will remain same. This is the procedure. Here, what are our key takeaways? Our key takeaways are that may be asked in gate are is OC test and tell on which side we do OC and SC test. We have to answer like this: OC test on LV side, SC test on HV side. OC test because of non-availability of that much voltage source. SC test because of power supply current rating requirement. Why core losses are neglected in SC test? Why? Because the required voltage for performing SC test is very less, and these core losses are dependent on voltage and frequency. Frequency is constant and it is rated, but voltage we apply is very less compared to rated voltage. That is the reason these core losses and magnetizing current, those are very less compared to copper losses. That is the reason why we neglect these core losses. And one more thing, we should not get confused. If someone says core loss are constant, we should know core loss are constant only when voltage and frequency are fixed or rated. And what are the cons of OC and SC test? Cons is you are getting R naught, X naught, okay, you are getting individual values, whereas this remaining R equivalent, X equivalent, you are not getting you are not getting primary, secondary side separately. You will get R equivalent, X equivalent, but you won't get what is R1, what is R2, what is X1, what is X2. In these two methods, we cannot find what is R1, what is R2 separately. And if someone wants to try, they can solve this problem. I will just simply, based on my past explanation, I will try to solve. Remaining, you can solve. Here, he has given 20 kVA 50H 2000 by 200 volts distribution transformer. From this, we can tell 20 kVA means 20,000 VA. From this rated current on HV side is 20 amps and rated current on LV side is 200 amps. Sorry, 10 amps. This is 100 amps. Here, what he has given is open circuit with HV side, HV open circuited. Means this is a transformer. He applied, he applied 200 volts. You can see in table 200 volts. Test on 4 amps current. Here they measured power 120 watts. We know from this we can find out R naught is nothing but R naught means which is compensating our core loss power by input current square. That is nothing but what is input power 120 by what is the input current 4 into 4. Here it is 120 by 16. In this way you can get R naught or R naught in OC side. It is nothing but 7.5 ohms. And you know what is Z? Z is nothing but 200 volts by 4 amps. It is nothing but 50 ohms. You know it is 50 ohms. Z is 50. R is 7.5. What is X? That is nothing but 50 square minus 7.5 square. This is nothing but 250 minus 7 point square. It is 193. Sorry, just let us revise this calculation. 50 square minus 7.5 square. 2443.75. And we have to do square root of 2443.75. Square root of 2443.75. That is nothing but here kindly see the calculation. It is 49.43 ohms. In the same method, he has given when SC test with LV shorted, we know VSC is 60 volts, ISC is nothing but 10 amps. 10 amps and input power is 300 watts. From here, you can calculate R equivalent is 300 by 10 square, nothing but 3 ohms. And X equivalent, we will find out. Actually, before finding X equivalent, we have to calculate Z equivalent. Z equivalent nothing but 60 by 10, 6 ohms. And X equivalent nothing but 6 square minus 3 square. This is 25. Is it 25? 36 minus 9. It is, sorry, 30, and you can get the value. Square root of 30. How much it is? 5.477. Now you got X equivalent and R equivalent. So these series parameters also you get. This is 3, this is 5.472. These are the values on secondary side. If you want to represent it on primary side, what is the equivalent circuit? We know these branches. What are the values? Here we calculated R is 7.5, R is 7.5, X is 49.43. 49.43, and R equivalent and X equivalent is nothing but 3 by, the ratio is how much? 2000 by 200. It is 10. Means 3 by 10 square, 100. At the same time 5.472 by 100. Further, we can simply draw this is the value. One side it is 7.5, it is 49.43, it is 0.03, it is 0.0572. All are in ohms. In this way you can solve, and remember these key takeaways so that it will be helpful in your GATE. Thank you.